So a very good afternoon to everyone. My name is Aryan, and in this particular presentation, we are going to discuss about a very important and interesting function which we call as the Dirac function. Dirac function has applications in various branches of physics. For example, electricity and magnetism. We use Dirac function to represent the point charge at origin. It also has various applications in quantum physics. We know Dirac was one of the pioneers in the field of quantum physics, and he has made tremendous contributions in the field of quantum physics. So it is very obvious that Dirac function has applications in quantum physics, namely to represent a pure state of position. We use Dirac function. We will talk about this application part in the second part of the video. In this particular presentation, we are going to discuss only about the mathematical formulation of Dirac function. Basically, what is its mathematical form, and we will discuss Dirac function in both 1D and 3D cases. So let us begin. So first of all, how is Dirac function defined? First in 1D case. So 1D means in one dimension. So in one dimension case, 1D case, how is Dirac function defined? So basically Dirac function is a function of x. Okay, so of course if we define the function in one dimension, so it only has one coordinate. You can either use x, y or z. So Dirac function is defined as del of x minus x naught. Okay, this is how the Dirac function is represented. It is represented by a simple del of x minus x naught. So basically it's a function of x. It's a function of x, and it is defined by the following 3 points. It is defined by the following 3 points. First point is that del of x minus x0 is 0 if x is not equal to x naught. If x is not equal to x naught, so this Dirac function is 0. Second point is that del of x minus x naught is infinity if x is equal to x naught. And third point is that if you integrate this delta function between minus infinity to plus infinity, this integral becomes 1. So at very first look, it's a very weird kind of function, and mathematically speaking, I don't think that this Dirac function satisfies the definition of function as far as the mathematics is concerned, but it is of tremendous use to us, the physicists. Now, what does this function mean? Okay, if I try to plot this function out, you will understand it much better. Let me plot this function. Okay. So this basically touches. Okay, so this basically touches this line. I try to just, this basically touches this. This is delta of x. Okay, and I should not use this, otherwise you will get confused. This is delta of x, and I have plotted it with respect to x. So it's just a straight line, and this point is x is equal to x naught. So this is the definition of Dirac function. You see, Dirac function of x minus x naught, this basically x minus x naught is the argument of the Dirac function, it is 0 if x is not equal to x naught. At this particular point, if I show you, at this particular point x is equal to x naught. Okay, it is 0 if x is not equal to x naught. So you see, at this point, 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 and so on, this point, this point, this point, when x is not equal to x naught, because you see at all these points x is not equal to x naught, so this function is 0. This function is 0. Now when x is equal to x naught, that is at this point, when x is equal to x naught, this Dirac function becomes infinity. Okay, this line, the straight line that I have drawn, it extends to infinity. And at right hand side of this point, where x is not equal to x naught, the Dirac function is 0. So red points, I would say, red points depicts the points where this x is not equal to x naught, and this Dirac function is 0 here. At this particular point, x is equal to x naught, where the Dirac function tends to infinity. And a very interesting thing, if you integrate this expression, that is the area under the curve, this del of x minus x naught dx, this is equal to 1. Okay, and you may find this very, very disturbing at first, because you may think that this is only just a straight line. ये तो सिर्फ एक straight line है. Straight line के अंदर, I mean, what is the area under this straight line? But this is how it is. Okay, and this is how it is. So I told you that it's not a very, very nice function. It's a very, very awkward function, awkward kind of a function, that this Dirac function is 0 at points where this x is not equal to x naught. That is, at all these red points, the function is 0, and this x is equal to x naught, the Dirac function tends to infinity. You can see this straight line, it extends to infinity, and the area under this curve, minus infinity to plus infinity, this Dirac function, if you integrate out this function is 1. Now you may think that where is this 1 coming from? It's a natural question, since at all the points the Dirac function is 0, so where is this 1 coming from? So it's very common sense that the contribution to this integral comes from this particular point, x is equal to x naught, because at all the rest points the Dirac function is 0, and this integration obviously means that area under the curve. So the contribution of this integral comes from this x is equal to x naught. So I may write this out. So the function, just a second, I may write this out, that so this function is 0 everywhere except at x is equal to x naught, where the function is infinity. The contribution to the integral obviously this third integral that I am referring to comes from the point x is equal to x naught. Now, since the contribution comes from this particular point x is equal to x naught, so we don't basically need to integrate this function from minus infinity to plus infinity. भाई क्योंकि कंट्रीब्यूशन तो सिर्फ x is equal to x naught से आ रहा है, तो हमें बिल्कुल माइनस इन्फिनिटी टू प्लस इन्फिनिटी इंटीग्रेट करने की जरूरत नहीं है. हमें सिर्फ पकड़ना है कि यार ये x is equal to x naught इस इंटीग्रेशन रेंज के बीच में आना चाहिए. तो फॉर एग्जांपल मैं इसे a से b के बीच में इंटीग्रेट करूं, तो ये x is equal to x naught पॉइंट आना चाहिए, क्योंकि जो कंट्रीब्यूशन है वो सिर्फ और सिर्फ इसी पॉइंट से आ रहा है इंटीग्रेशन का. तो कोई फायदा नहीं है कि यार मैं माइनस इन्फिनिटी टू प्लस इन्फिनिटी के बीच में इसे इंटीग्रेट करूं, है ना, obviously because the contribution is only coming from x is equal to x naught. So this also becomes a mandatory condition कि ये प्रॉपर्टी सिर्फ और सिर्फ तभी वैलिड है जब इस रेंज के बीच में x is equal to x naught हो. यहाँ पर मैंने ये बात मेंशन इसलिए करी बिकॉज ऑब्वियसली ये जो पॉइंट है एक्स नॉट इट वुड डेफिनेटली बी विद इन माइनस इन्फिनिटी टू प्लस इन्फिनिटी। यार माइनस इन्फिनिटी से प्लस इन्फिनिटी के बीच में तो एक्स नॉट होगा ही, बट टू बी more precise you can integrate this expression. ये integration you can use between a to b also. The only important condition is that this point x naught which I have written in this function should be between this integration limit. So I may use this that you can integrate this expression between a to b del of x minus x naught dx. This is also one. The only condition being that this x naught should be between a and b. Otherwise, this function is 0. Obviously, if this you may also integrate this Dirac function maybe between this and this c to d. You may also integrate the Dirac function between c and d. But then at all the points except this x is equal to x naught, the Dirac function is 0. So therefore the integration would be 0. So if you want this integration to be 1, choose points these limits a and b such that this point x naught is between the a and b. So sorry, this is sorry, yeah, otherwise is 0 otherwise. Okay, now we have got this. Now I also want to prove a very important result. Okay, and that important result is if you want to integrate this Dirac function but you multiply a function with it. Let's say you integrate this Dirac function between x1 to x1 to x2 and you multiply it with a function. So maybe this dx. Okay, so here you are only integrating the Dirac function, but here I have multiplied a function f of x and I am then multiplying it with Dirac function. So what would be its result? The result will be f of x naught. That you just have to put this x naught instead of x and this would be the result. Now why so? The reason is, and I may say, it's a very important property. We will discuss other properties in the next video, but in this particular section I will only discuss this particular property as this is a very important property. So you multiply this f of x with the Dirac function and you have f of x naught would be the answer. Why? Now here also the condition is that this x naught should be between this x1 and x2. Now you see, obviously consider, okay, let's say this x is not equal to x naught here. Okay, if x is not equal to x naught, then obviously you may say that if x is not equal to x naught, then from the property of Dirac functions we know that if this x is not equal to x naught, this Dirac function would be 0. Yeah, look at this property. Look at this property here. If this sort of here, yeah. So if x is not equal to x naught, then the Dirac function would be 0. Yeah. So here, if this x is not equal to x naught, for all the points where x is not equal to x naught, so the Dirac function would be 0. Therefore, the integral would be 0. So no contribution from the points where this is. So I may write if x is not equal to x naught, the Dirac function, you may say this particular integral x1 to x2 f of x del of x minus x naught, this will be 0. So where is this answer f of x naught coming from? Very obviously it is the answer of this integral f of x naught is coming if you put x is equal to x naught. Because what happens if you put x is equal to x naught? So if you put x is equal to x naught, obviously this f of x becomes f of x naught. क्योंकि यार फंक्शन की यही डेफिनेशन होती है कि अगर आप x की जगह x naught डालोगे तो यहाँ पर ये f of x naught हो जाएगा. Therefore this f of x becomes f of x naught. And now just substitute the value. Okay, so this would be integration x1 to x2 ये एफ ऑफ एक्स जो है अब एफ ऑफ एक्स नॉट हो जाएगा, क्योंकि हमने पहले वाले केस में डिस्कस करा कि यार मान लो ये जो भी मैं इंटीग्रेशन परफॉर्म कर रहा हूँ इसमें जो x है ये x नॉट के बराबर नहीं है। यार दो ही चीजें हो सकती हैं, या तो x x नॉट के बराबर नहीं है या x x नॉट के बराबर है। पहले वाले सिचुएशन में x x नॉट के बराबर नहीं है, यानी सारे के सारे पॉइंट्स आ गए जहां पर x x नॉट के बराबर नहीं है। वहां से तो कुछ कॉन्ट्रीब्यूशन आ ही नहीं रहा है इंटीग्रेशन का, तो वहां से तो इंटीग्रेशन जीरो आ रहा है। तो ये एफ ऑफ एक्स नॉट आ कहां से रहा है आंसर? ये दूसरे वाली पर्टिकुलर चीज से आ रहा है, जब आप x को x नॉट के बराबर रखोगे। अगर आप x को x नॉट के बराबर रखोगे, obviously this f of x will become equal to f of x naught. So this will become f of x naught del of x minus x naught dx. Now obviously what this becomes, ये f of x naught तो constant है क्योंकि इंटीग्रेशन तो x की लिमिट में है। ये f of x naught means one particular point। तो एक फंक्शन में आपने एक पर्टिकुलर पॉइंट की वैल्यू डाली तो that becomes constant, so I can take it out of the integration. Integration only remains between x1 and x2. Okay, and this is del of x minus x naught dx. And I have stated earlier that this x naught point is between the integration limits x1 and x2. So what happens to this particular integration? I mean, what is the value of this particular integration? Yes, ladies and gentlemen, you guessed it right. This is 1. So therefore, answer only remains f of x naught. Right? We know from the property of Dirac function that this is 1. So therefore this is a very important property, and there are lots and lots of basic numericals that are asked regarding this property. Like for example, very important, like for example if I give you one numerical that this integration is between 2 to 4 and you have x square and you have delta of maybe x minus 3 dx, what is the answer? Obviously this f of x in this case is x square. Yeah, and does this x naught come between the integration limit 2 to 4? Yes, 3 comes between 2 to 4. So what is the answer? We know from the above property that answer is f of x naught. You know what is f of x? What is x naught? X naught is 3. Therefore the answer is 3 square is equal to 9. If I give you the same numerical and I say 2 to 4 x square del of x minus 5, what is the answer in this case? This x naught which is 5 does not come between 2 and 4. So what is the answer? Answer is 0. Square. Okay, so this is about the Dirac function in 1D. So on the similar lines, you can have Dirac function in 3D. So for example, or you can say similarly, you can write Dirac function in 3D, because very obviously in 3D now, like हम जो हमारा जो वन डायमेंशन का जो केस था, वन डायमेंशन के केस में हम लोग जो डिराक फंक्शन है वो सिर्फ x का फंक्शन था, है ना। ऑब्वियसली जब हम डिराक फंक्शन 3D में बात करते हैं तो इट्स अ फंक्शन ऑफ स्पेस पॉइंट्स, है ना। यू कैन से इट्स अ फंक्शन ऑफ स्पेस पॉइंट्स। और स्पेस पॉइंट से मेरा मतलब है एक नॉर्मल क्या कहते हैं, स्पेस पॉइंट को हम जो नॉर्मल हमारे जो वेक्टर 3D है उसमें हम एक वेक्टर से रिप्रेजेंट करते हैं ना। तो स्पेस पॉइंट कैन बी रिप्रेजेंटेड बाय अ वेक्टर। बाय अ वेक्टर प्रोबेबली r। तो हम कैसे डिफाइन करते हैं, हम बोलते हैं इसमें हम सिर्फ डेल यूज नहीं करते, हम डेल क्यूब यूज करते हैं। वी से डेल क्यूब ऑफ r माइनस r नॉट, इसको ऐसे रिप्रेजेंट करते हैं। ठीक है। और इसकी जो डेफिनेशन होती है वो अगेन वही चीज होती है जो मैंने आपको पहले एक्सप्लेन करी है कि सिमिलरली जैसे हम वन डायमेंशन के केस में था ना, सिमिलरली वैसे ही कि डेल ऑफ आर माइनस आर नॉट। अब ये ध्यान रखना कि ये जो आर है ये सिर्फ वन डायमेंशन में नहीं है, ये एक वेक्टर है थ्री डायमेंशन में, बिकॉज obviously we are talking about Dirac function in 3D, so you don't have just one point. Okay, you have a coordinate xyz, and that coordinate xyz can be represented by a vector. So this del of r minus r naught is equal to 0 if r is not equal to r naught. Okay, in second case you have del of r minus r naught is equal to infinity if r is equal to r naught. Third case, this del of integration all space, because remember now we are not integrating between the points since we are talking about 3D. So in 3D we integrate over an entire volume. Okay, so this del of r minus r naught over dv, this is equal to 1. Like we had del of x minus x naught dx is equal to 1. Similarly, since we are now integrating over the volume, so we are taking a small volume element dv and we are integrating over the entire space. Yeah, and again again like we did previously, where is this particular contribution coming from? Okay, since at except at r is equal to r naught the function is 0. If r is not equal to r naught the function is 0. So where is this contribution 1 coming from? It obviously comes from the point where r is equal to r naught. And if the contribution is coming only from the point where r is equal to r naught, so it doesn't matter that we integrate over the entire space. The only mandatory condition remains that you integrate between the limits जहां पर ये जो r नॉट है ये इंटीग्रेशन लिमिट्स के बीच में, ठीक है। तो मैं बोल सकता हूं इस सिचुएशन में भी दिस कंट्रीब्यूशन टू द इंटीग्रल comes from point r is equal to r naught. Okay, so we can say that you integrate between the volume this del of r minus r naught dv, this is equal to 1 if your r naught comes between the, let's say, any point, okay, r1 r2, any arbitrary point. If, or I can say if the volume contains this particular point r naught, then the integration is 1, otherwise the integration is 0 otherwise. Okay, now you can represent this Dirac function in 3D in terms of Cartesian coordinate. You can say in terms of Cartesian coordinates, you can represent this Dirac function del cube of r minus r naught as, you can represent it as del of x minus x naught, del of y minus y naught, del of z minus z naught. And in terms of spherical polar coordinates, how this Dirac function can be represented? At first, naively we may say that this can be represented as del of maybe r minus r naught, del of theta minus theta naught, and del of phi minus phi naught. But this is not correct. Okay, this is not correct. The representation in spherical polar coordinates is a factor of r square sin theta. You have to also include a factor of r square sin 1 over r square sin theta, and you can use this del of r minus r naught, del of theta minus theta naught, and del of phi minus phi naught. Okay. This is how you can represent del cube of r minus r naught in terms of spherical polar coordinates. And if you have to verify this, okay, that this is correct and this is not correct, you know this particular property that if you integrate this expression out, this integration would be 1. Yeah, from this you know if you integrate this over the entire volume, the integration would be 1. Let's integrate out this expression. Let's integrate out this expression. If you integrate del cube of r minus r naught over the entire volume, this is, you integrate over r is equal to 0 to infinity, you integrate over theta which is 0 to pi, and you integrate over phi which is 0 to 2 pi, and this is 1 over r square sine theta del of r minus r naught del of theta minus theta naught del of phi minus phi naught, and the volume element in this particular case is r square sine theta d theta d phi. This r square sine theta cancels off, so the individual integrations you can write it as r is equal to 0 to infinity 0 to infinity del of r minus r naught, then integration of theta is equal to 0 to pi del of theta minus theta naught, and integration phi is equal to 0 to 2 pi of del of phi minus phi naught, and this, the individual integration, this as we all know will be 1. Okay, because these are the extreme limits, and obviously this r naught has to come between this 0 and infinity, this theta naught has to come between 0 and pi, and this phi naught has to come between 0 and 2 pi, because these are the extreme limits of the variable r naught, theta naught and phi naught. So this comes to be 1. So basically the result is verified. So these are the basic properties and basically the basic mathematical formulation of Dirac function. In the consecutive lectures we will discuss few more properties of Dirac function, as well as we will discuss about some of the applications of the Dirac function. Okay, till then take care, bye bye, thank you.